Hi everyone, today me and Ryan will be doing a demonstration for lab E3, which is the Charlie vaccine and ADC conversion. Right? So for part 1, this is basically the circuit for our part 1, which is the Charlie Plex LEDs. So we move to the coding. Here is the coding for the Charlie Plex LED. So we define pins for our inputs and outputs. So this is the delay function, and here is the LEDs where we set PDDR and PSOR for each particular LEDs from 1 to 6. This is how the Charlie Plex works. Here's the logic behind it. So we initialize our Charlie Plexing here, where first we set a pin control register for our output and input. For the output, we remove the pull enable and the priority set, because output is already sufficient with the high drive strength where current can flow through. We remove the PE and PS because it may leak some current. Alright, so here's the main function to run. Here's the for loop. We end our PDIR with our pin, so that to make it as input. Alright, so let's debug this program. So this is our circuit. So we are using active flow for our input. So basically, before we move into our circuit, I would like to say that this one, for active flow, for the first time, I mean, initially the input will be 1, as the current will be flowing from the VCC to 1. And when we switch, we close the switch, it will turn out to be 0. So this is basically how active law working. So we implement it into for our input. So move to our circuit. This is our circuit. As you see that I'm not using a switch because the switch is not working correctly. So instead I use this manually using my hand. So as you can see, this one is plugged into our MCU. This one is the input into the MCU. So here's the switch. So initially it's 1, which is because we connected to the MCU. So if we unplug it, it will be 0 since we are using active flow. So when the circuit is 0, 0, 1, the first LED will light up. The first LED will light up. Then when 0, 1, 0, the second one will light up. When 0, 1, 1, the third one will be lights up. And when the fourth one is 1, 0, 0, when 1, 0, 1 will be the fifth one. So for the fifth LED, we will be 1, 0, 1. The fifth one. To get 6, we'll let our input as 1, 0, 1. 1, 0, 1, 1, 0. Yeah, 6. Okay, that's for our part 1.
Hi, I'm Ryan. So today I'm going to present about our Lab 3 Part 2. So basically this is a block diagram for ADC channel. This is a section 1 and section 2 over here. Section 1 is measure the voltage level, and we go to the spot. This is a delay function, and then following with initialize ADC. So over here we set all ADC register to 0, and then this one is set to 2 because we are using 10-bit differential mode. Then so after set to 0, we set this mode to channel 14 because we are using channel 14, which is direct connected to port C pin 0. And then next with calibration ADC. So we set a normal power configuration for safety 1, clock ratio to 1, short sample time and mod 0, and for the bus clock we set it to 0 because we're using bus clock. For SC3 we set it to 1 conversion, enable the hardware average. Then we're using 32-bit sample average. So for SC2, this code means we enable the software trigger, and for the SC3 we trigger the calibration, and then this is where calibration begins. And this cocoa mass is equal to 0 means that calibration success, and then this is fail. So next, for the conversion part, we select the mode to 0E as hexadecimal because we're using a channel 14, ADC channel 14. And then cocoa mass, wait for conversion complete. This line here is read the data to our variable result. And for the main function, we declare this 3 variable as integer because we can't use floating through our lab manual. It's stated that doesn't work in floating point. So we enable the ADC clock, call the function, initialize, and then this is calculation of voltage level. So first, the ADC data is equal to our conversion, the value that we get from the ADC, and then the voltage one is for the first decimal of our voltage level. So the step basically you show it over here. Voltage one is this one, the first value. So you get 2 power of 10 divided by 310. 310 we get it from here. 2 power of 10 divided by 3.3 volt. So this is our first value. Our remainder over here we get we divide again. We get a second value as integer, and then this is our third value. It's 0.3, but then we declare as integer, so we can't show the decimal of 3 over here. So back to code. So our printf value, we show it kitty letter. Let's debug. Okay, so this is 5K is full, so the resistivity is full from this variable resistor, so it's 3.3 volt over here. So when we turn it,
better.
okay, so this is a maximum resistivity, so it's equal 3.3. If I turn it anti-clockwise, the resistivity will decrease, and then from the output here you can see the voltage level. So maximum anti-clockwise with resistivity with 0 is equal to 0, so the voltage also equal to 0. Okay. That's all for part 1. Thank you. Hello, it's me again. So I'm going to present part 2, section 2 to measure the light level. This is a delay function. Initialize ADC as usual. It's similar with the part 1, and calibration and conversion. It's a bit different. This conversion is a bit different from our section 1 because we're using channel 19, which means 13 hexadecimal is specified for light sensor to measure the light level. And this comes the main function. So the sequence of the main function also same with section 1. Just that we print the value, the light level directly is equal to the ADC value over here. Let's debug. So the light level is approximately 900 when I'm not applying any torch or light intensity to the sensor. And then when I'm applying the light over here, so the result turns low to 61 because we can't adjust the brightness of my cell phone, so use a distance to measure the light level. As you can see, the light level is increased slowly. So that's all for me. Thanks.
Hi, it's me again, Dexter here. So what I'm going to do is the part 3 right now. So basically for this part, we're just combining part 1 and part 2 for the light sensor with the multiplexing. So in this program, we are just basically implement the to run our multiplex LEDs. So this is the coding, and here is where we define our pins for output and inputs, the delay function, the LED, and then the initialize multiplexing, calibrate ADC, like earlier on, initialize ADC to ADC conversion as well. So here is the main function. So first of all, we just do the declaration for the variables, like how we did for the voltage in the part 2 mentioned by Ryan. Here's the calculation, and here the main thing that I want to highlight here is the data collected from the ADC will be divided into 6, as we are using 6 LEDs for our multiplexing. So we divided into 6, so we get range from 0 to 170, and then from 171 to 340, 341 to 511, 512 to 681, and 682 to 852, and so on. The last one till 1024, which is 10 bits. Alright, so let's just debug this program. So initially the voltage level will be high when the light level is low. So when I put when I flash the light near to the light sensor, we're getting a lower voltage. So as I increase, so this will be lighting up the first LED. So as I increase the distance, it will light up sequentially with the logic of Charlie Plex LEDs. So here it goes. 1, 2, 3, 4, 5, and 6. Yeah. So that's all for my part. Thank you.